We are now going to take a look at the short run behavior of rational functions, and there is an exploration sheet to go with this topic, so make sure you have that in front of you. Before getting started on the sheet, we just want to review some things that we've talked about in the past when we were dealing with, I think, some of the trig functions, that anytime you have some constant number over an increasingly large, either positive or negative number, right? Such as, here's an example, this fraction is very, very small, right? So anything like this is going to be approaching 0. Whoops, need my pen out here. All right. And if we have some constant over a decreasingly small, either positive or negative number, such as something like this, which would be the same thing if we wrote it in fraction form as 1 over, 1 followed by a lot of zeros. This is either approaching positive or negative infinity, depending on how the signs are working out. So, the main idea is if you have a very small number in the denominator, that means you have a very large number for your fraction. Okay, and if you have a very large number in your denominator, that means you have a very small fraction. You should have a pretty good graph if you plug this formula in as f1 of x on your calculator and just use a standard window. And once you have that, we want to use the graph trace option to set the cursor at x equal to 3. Why don't you pause the video and do that right now? If you did things correctly, you should actually see that the calculator is giving you undefined at x equal to 3. Let's explore why that is. Pause the video as you plug 3 into the formula and see what you get. Is this it? Hopefully it's pretty obvious why we got undefined on the calculator, right? Since we have 0 in the denominator. Let's take a look at other aspects as well, though, of what's going on for values of x close to 3. Since x equal to 3 is causing the denominator to be 0, it's a pretty key number. And you can see when we factor the denominator that x minus 3 is one of our factors. So you should probably suspect that this factor of x minus 3 is probably playing a key role when we have numbers close to 3. Let's check it out. There's a table on your sheet that we would like to fill out by using the calculator to get some values. So we want to get some values for that factor that's in the denominator, x minus 3, as well as the function. So go ahead and enter x minus 3 as f2 of x, and then you're going to go to a split screen table. You can access that by hitting your menu button and going down to table, and then it'll give you the option of split screen table. And once you have pulled up the table, you can actually grab this center line and move it to the left to make the table a little bigger so that you can see 3 columns, your x column, your f of x column, as well as your x minus 3 column. And once you've done that, you can hit the menu button again while you're on the table option, and then go down to, go to hit 2 for table and then edit table settings. And once you're in there, you're going to change the independent mode to ask as opposed to auto, because we want to be able to type in our own x values. And so just hit OK, and you should see that your x column is actually blank, and you can type in the values that you see in the table. You should pause this video to carry that out. All right, hopefully you got the following results. Hopefully you can see from your table values that the closer and closer your values get to 3, right, the larger your output values are for your fraction. And of course that's because your denominator keeps getting smaller and smaller, right? Because x minus 3 gets to be a very small number. And you certainly feel free to get even closer to 3 if you'd like, but I thought these numbers would demonstrate this pretty well. And of course, since our y values are getting either to be very large positive numbers, very large negative numbers, this is creating the phenomenon of a vertical asymptote, right, that we have seen before on some of the trig graphs that we worked with. So just as a reminder, right, vertical asymptote occurs when f of x is undefined, when we have 0 in the denominator, while the numerator does not equal 0. We'll make more of that in a few minutes. Okay, as x approaches c from either direction, f of x approaches either infinity or negative infinity. And we've already seen this notation before. The graph actually never touches that line x equal to c. It just comes closer and closer to it, right? Because we are undefined right at that value for x. So now we're going to kind of repeat what we just did, but instead of doing it at x equal to 3, we're going to do this at x equal to negative 2. So pause the video, go back to the graph on your calculator, and see what value you get from the trace button at negative 2. And then plug negative 2 into your function and see why it's giving you that. All right, is this what happened? Hopefully you saw your calculator say undefined at negative 2. And we can see why when we plug the negative 2 in, right? Once again, we'll have 0 in the denominator, and that would make this undefined. But notice we did also have 0 in the numerator. Perhaps I have these two parts backwards a little bit. I asked the question why. If you go back and look at the graph, you'll notice there was only one vertical asymptote, and that was at x equal to 3. There is not one at x equal to negative 2, and the question is why. Perhaps simplifying the formula for f will give you a glimpse into the answer to part 3. Pause the video and give that a try. Does this make sense? Yes, certainly once you simplify it, right, cross out the x plus 2's, then negative 2 is no longer going to cause there to be a 0 in the denominator. So essentially it appears that the graph of f should be the same as just 1 over x minus 3, which only has a vertical asymptote at x equal to 3. So now let's plug in g of x, this 1 over x minus 3, in as f3 of x, and see if there is any difference between the graphs of our original function f and this new function g. As you can see, the suggestion is to take a close look at what's going on at x equal to negative 2. So pause the video and give that a try. If we just glance at the graphs, we can see they do look pretty much identical. But a closer look right at x equal to negative 2 reveals their difference, right? We are actually getting a value back for g of x. This is g over here. And we are still not getting a value back at negative 2 for f of x. So these two functions are not the same function. They are not the same set of ordered pairs. We are very used to, from algebra classes, factoring and simplifying, so we can do that. But we need to remember that f of x actually does not equal 1 over x minus 3. Because if we plug in negative 2, we still need to get undefined, and we would not get undefined here, right? If we plug negative 2 in, we would get 1 over negative 5. So f of x does not equal 1 over x minus 3. It does, however, equal 1 over x minus 3 such that, this is the such that bar, x does not equal negative 2. G of x, we can call a new function. That can equal 1 over x minus 3, but these are different functions. They differ by 1 point. So how do we handle a graph such as, such as f of x here when we get to negative 2? Because we should indicate something about that point not being there. So what we do is we draw a little circle right at negative 2. Okay, and what's good is to draw it ahead of time so that when you sketch your graph, you stop at the edge of the circle and then pick up on the other side. But we just leave a little hole there. And when you see a situation like this, you will know to call this removable discontinuity. Of course, it gets its name from the fact that you can actually remove that discontinuity from the formula if you simplify, but you do need to remember it's still there. A vertical asymptote, by the way, is also a discontinuity, okay, because there is a break in the graph there as well. It, however, is not removable. And those are the two basic types of discontinuities that you usually see in graphs. Okay, so here we have removable discontinuity to x equal to -2, because the part of the denominator that was undefined can be removed when the function simplified. Removable discontinuity does show up as a hole in the graph, not as an asymptote. So let's finish this video by taking a look at this example in number 2. Can you determine, without looking at the graph, whether h has any vertical asymptotes? Before you quickly declare yes at x equal to -4, because that would make the denominator 0, I will point out that if you plug -4 into the numerator, you will also have 0 on the top, and that would be that 0 over 0 situation, which I don't think led to a vertical asymptote. So see what you can do with this numerator before you decide whether there's a vertical asymptote or not. Pause the video and give that a try. And once you've done that, then see if you can answer the last two questions. Okay, see if this is what you got. So if we factor the numerator, we can see that we do have two factors that can cancel, right? And that would just leave us with x minus 4. However, let's not forget that x cannot equal -4, right? Because that was causing the denominator to be 0. So -4 is not going to be a vertical asymptote, right? Because we were able to remove that from the denominator. So what is the shape of the graph of h? Well, yep, it's simply a line, right? It's just the line x minus 4, all right? And then, let's see, we'll just write y equals x minus 4. And what is the domain of h? Well, you might say it's all real numbers, right? Because that's what this line's domain would be, but we do need to remember that x cannot equal -4, because that would cause h to be undefined, right? H of -4 would equal 0 over 0, and that is undefined. A quick look at the graph on the calculator shows, yes, it's just the line x minus 4. And then if we use the trace option, we can actually see that at -4, our function is undefined. This video is going to stop right here for now at the midway point of this exploration, but there is another video that will go through some of the examples from number 3.